Hello, this is Wade Tabor with RefracTech. This presentation deals with some general refractory concepts for cylindrical linings, as well as some very specific issues for syngas and hydrogen applications. This presentation was originally presented by me at the Syngas Syndicate conference that took place on October 25th, 2023 in Houston, Texas. You'll be able to find website and contact information in the video description, as well as on the final slide of this presentation.
All right, so just by way of introducing myself very quickly, I have 33 years, I think, this year in refractories. Had a family company who did installations. I was a bricklayer for a number of years. Put myself through school, got an engineering degree in ceramics and refractories. Worked for a variety of refractory contractors. Went to work for almost 10 years with Boudouard, where I learned the gasification business and supported that worldwide. Then took a tenure with GE Gasification, where I moved beyond refractories and got involved in a lot of other hardware designs, feed injectors and the like. Left there, I went for another gasification company, Synthesis, a fluidized bed unit, VP of engineering. But for the last 6+ years, I'm on my own, and I don't tuck my shirt in any longer. All right, but why? Why are we having second, third presentation on refractories? So there's a pretty big impact here on your syngas operations. So we understand that syngas is a precursor to your chemicals production. You could be producing, $1 million plus a day of downstream product. I know that's the number that Radial sometimes uses when they aggregate, QE1 and everything else. So it gets pretty expensive when your refractories become unavailable. Couple that with the fact that, obviously the lining costs money, but it's not any kind of multiples of the downtime. But it could be, $500,000, $1 million, 1.5, depending on the size of the vessel. But the main issue is, already been touched on, is the lead times can be quite high. We're talking about very specialized, it's not commoditized shapes, very specialized shapes that have been designed to work in these reactors. So to Fred's point, you got to have a plan, right? We're not going to solve an issue just showing up and saying, what's your problem? I can fix it today, right? Ultimately, even when we get the materials on site, the refractory installation of the unit could be a month, could be 2 months. So that downtime, that unreliability that could be a part of the refractory makes it be one of your highest OpEx, CapEx loss contributors if you don't have this handled right? Over several refractory service lives of linings, you could lose hundreds of millions of dollars of production, if that represents 3, 4, or 5 months of operation over the course of a 10-year period. And certainly some in this room have probably realized some of those numbers. But let's talk about what makes this process special. I'm not going to delve into all the reactions, but I want you to realize it's complicated, right? There's not one or two things going on inside the POX reactor. And I'll say POX, obviously it could be an autothermal reactor, it could be a steam methane reformer. A lot of these reactions are in common, depending on pressures, depending on hydrogen to CO ratios, all these different things. You might pick a different technology, but I think generally in the room, we're all coming from the gasification POX environment. So recognize that, the top couple of reactions are your combustion reactions. We put in a stoichiometrically limited amount of oxygen to give you the exothermic heat that drives all the other reforming and shift reactions that produce syngas. What becomes important about this is realizing that these reactions don't just vary, linearly down the unit, right? They're in constant. These are all, or most of these are all, equilibria reactions, right? So at different temperatures, different zones where the energy is present, where the molecules are present, these reactions are constantly shifting back and forth between CO and CO2, hydrogen and water, steam and methane, and the like. So again, it's not linear, and that's not a good way to think about it, right? Ultimately, you can think about it as you have this oxidation zone coming out of the burner, but that oxygen is consumed, right? There's no other oxygen coming out with the syngas. And all these other reactions kind of shroud this oxidation zone, depending on how much energy they're getting from the oxidants and whether those various equilibrium reactants are available to produce the products. What becomes important here is you need to make sure you have a good handle on process volume and flows, right? Because it's very possible that if your flows get out of whack or don't coincide with your process volume very well, you can start to squeeze out physically the space where reactions can occur. So where your process thermocouples in the middle section of the unit might be measuring, 24 and 2500 degrees Fahrenheit, your oxidation reaction is well above 3000 degrees Fahrenheit, right? Well above the potential to melt every brick you have inside the unit. So if you extend the oxidation too far down into the vessel, like in the cone and throat areas drawn in this quench unit, that I've seen many times, process thermocouples look normal, but the throat's been melted because there's no room for these other shrouding reactions that take the temperature away to occur. You're oxidizing on the cone, you're oxidizing on the throat, and you start to melt materials. So there's a lot going on here, and there's a lot more variability inside the space than what one might imagine. And I think that's an important concept to understand. When we talk about the various reactions that can be deleterious to the process based on syngas and based on these different thermal differences throughout the elevation and throughout the unit, one thing we have to realize is we can't make the unit too cold, right? Nozzles, flanges, feed injector nozzles, thermocouple nozzles, anything that gets too cold where the inner vessel wall drops below the dew point temperature of the syngas, you're going to, just like condensation on your soda can, you're going to produce a liquid film. But that liquid film in the syngas environment, depending on the species that are available to it, could become hydrochloric acid, carbonic acid, ammonium chloride, many other different things that can cause pretty deleterious metal loss to the vessel. So in fact, this is a picture just of this last year at a solids gasifier where their top dome got way too cold. The refractory installer switched out the type of castable that was above the dome. They said, well, we're going to put in bubble alumina, and it made the dome way, way too cold. And in fact, they lost over an inch of metal up on their top head and had to completely go back in and re-weld and machine back. This process was about 3 months of downtime for them to retrograde the top head of their vessel. So it's an issue that you have to be wary of. You can't be too cold. Kevin mentioned this. The reason why we use high alumina refractories is because hydrogen, dry hydrogen specifically, is very capable of reducing silica, which is a very common material, not necessarily impurity. The high aluminas, it could be an impurity, but it's a very common material inside refractory materials. So your insulating bricks, your super duty bricks that are used in the outer segments of the lining, those tend to be safe because they're at lower temperature and below the reaction zone. What we would do to evaluate is we'd pull up like an Ellingham diagram, and you look at the temperature that you care about that refractory sits in, and you look at the particular oxide that you're concerned about hydrogen reducing, and then you have to look at the partial pressure of the hydrogen. And that's what dictates whether or not the hydrogen will reduce that compound. Incidentally, the way the Ellingham diagram works is you're looking at a ratio between the partial pressure of hydrogen versus the partial pressure of water. Again, dry hydrogen reduces much more effectively. So what we end up setting ourselves up with is something like a solids unit that has slurry and a lot of water going in with the feedstock tends to have a higher partial pressure of water than some of the natural gas POX units. So they actually don't have to worry so much about the hydrogen reduction, but they have to worry more about the dew point corrosion because their partial pressure of water drives the dew point temperature that I previously talked about. So these two slides I presented are kind of yin and yang. It's kind of you have a problem with one or the other, not typically both unless you're at substantially high pressures. But again, many epoxy units operate well in the range. 1400 degrees C here. It's a typical epoxy operating temperature. And if you're about 4 times higher in hydrogen than water, in terms of order of magnitude, then you're going to reduce these bricks. So this is, the intermediate layer of a unit that was, these bricks just fall apart. Looks like little mountains of snow, right? The bricks just crumble when you touch them. And as Kevin pointed out, this material, the silica that was carried off, it goes somewhere, right? It becomes gaseous silicon oxide. When this cools in your waste heat boiler, it flakes out and it starts to form deposits and solids. And it starts to clog up your tubes. It becomes a big issue. It's not only deleterious in the refractory, but it clogs up your downstream components. Tim mentioned the Boudouard reaction. Boudouard, actually, if you go back to the, it's the decomposition or the equilibrium of CO and CO2 that occurs inside the epoxy unit. And it was actually on one of my first slides where I showed you all the epoxy reactions. You actually count on this in reverse to reform the CO2 into CO. The problem is when your CO partial pressure becomes high enough in a temperature band of about 500 to 1,000 degrees C, that catalyzed by iron impurities in the refractory, we can actually start to convert the CO back to CO2. And because most of your epoxy units still have anywhere from 5 to 10% CO2. So when the CO2 is formed, it forms with it another molecule of carbon. The carbon, this 500 to 1,000 degree temperature band I'm talking about, is not on the hot face, it's not in the process volume, it's in the backup lining of your refractory. And so this carbon deposits in the porosity of the refractory. Materials that have high iron contamination, which castables tend to have more of, just get completely torn apart. So here's a couple of pictures of the castable layers inside the refractory, right? There's a hot face here that's completely untouched. But inside the depth of the refractory, here's a castable body that's just completely carbon-filled. That was snow white dense refractory before it was put in. After a couple of years, dig it out with my hand quite easily. This is what the Boudouard carbon swelling. The carbon is known to swell that refractory about 20%, which just, anything, the ceramic is inflexible, right? So when you swell it 20%, it falls apart. One of the solutions in the recent years, again, castables are difficult to get rid of. There's areas where we have to use them to meet certain tolerances or the shapes can't fit tight enough against a hemispherical head or something. So we've actually found that some of the chemically cured castables that have an acidic binder system inside them, that acid actually eats and neutralizes the iron catalyst. So in fact, castable that's been in service for 3 or 4 years now is coming out in large white chunks and kind of battling and understanding how to get rid of some of this Boudouard reaction that we're seeing. So in many of your units, as we've worked on retrofits, we've moved to chemically cured castables. I'm happy to say that, maybe it's premature to say, but I'm working with Saint-Gobain now to work with them on chemically cured castables because they offer capability of using some of their bubble alumina and other mixes to move to a chemically cured species so we don't have to sacrifice things like thermal conductivity to get this benefit of getting rid of the Boudouard carbon. So understand, if it's not clear, many of you know, in a epoxy unit, natural gas, you're not wearing away brick, right? We're not thinning out the brick over time. That's not the end of the service life for you guys. What it is it's the up and down thermal cycles where the joints become misaligned, and we'll talk about that. But it's also the formation of this Boudouard that crushes up the outer materials and forms gaps. And when you start to have too many hot spots because you got too much carbon in that unit or too many aligned gaps, that's your end of service life. So these are the things we have to address in most of the units represented in this room. So I kind of indicated, so the heat transfer calculations are important. Right? We can't be too cold, we get dew point. We can't be too hot, we damage the refractory. Right? And all the differences in between. So we have to understand that with the designs of these units, the things that were mentioned before, the hydrogen content, the molar volume percentage, the partial pressure, it influences the thermal conductivity. In some cases, it can double the thermal conductivity of a highly porous material. We have to understand that. We have to be analyzing the heat transfer of these reactors, with the fiber properly compressed in its use state, not in its installation state. That could throw us off by 100 degrees or more. We have to have the appropriate boundary conditions. Comes back to the issues of temperature measurement and how precise those can be and where the thermocouples are located and where those reaction zones are located, right? So we use things like FEA and a lot of time-proven methods now to correct the material properties for complicated geometries to get these areas correct. Everything beyond this point, getting the thermal expansion correct, getting the movement around other components, all these things, is all about getting the temperature estimations of the various layers correct. Just like I mentioned back in A&A's pitch, where the temperature of the lances of the feed injector affect concentricity and affect, retraction, right? We have the same issues here with refractor to make sure something's not pressing on something else. One immovable body breaks another immovable body, gives you a gap, gives you a hot spot, shuts you down, forces an outage. So radial thermal expansion is something that's important to talk about because you have multiple ring segments, usually refractory shapes, that form the bases of these cylindrical vessels you're putting the refractories inside of. And there's a couple of schools of thought in terms of how one should handle radial expansion. This is the first. Many kind of European design houses have taken to do based on other applications. This, by the way, this is a perfectly valid in some applications. I'm going to tell you why it's not valid here as a preview. But in some applications, it's perfectly valid. But what they taught in some of the units that you have operating at your vessel, at your facilities, is that every few bricks, we're just going to make an open joint. We're not going to mortar them together. In fact, they have this scheme of putting oil paper just over that joint so the bricks can slide, which I don't understand because ultimately the entire length of cord of the bricks grows, not just the last little end of it. So I don't understand putting the slick stuff just underneath the opening, but they put these periodic joints. So first understand that when we design the thermal expansion of the refractory layer, we're designing to design conditions, right? So for most of your units, we're going to design that for 2,800 degrees Fahrenheit because we don't want the thermal expansion to fail and your bricks to break if you had an excursion, beyond that point up to some point for some period of time. But you guys don't operate at 2,800 degrees. You operate at 24. You operate at 25, which means if I design these joints for 2,800, all these joints are open when you're at 24. They may have closed partially, but they're still open. So gas is flowing. What we typically do in these joints is we try to pack them full of fiber. Fiber is full of silica. Silica is eaten by hydrogen. Fiber doesn't last. You have joints that are open through your refractory lining. It's an issue. So what we've done more historically, and correctly I think by that, is we put these concentric gaps behind the layers. So we can take up the differential radial expansion between the hot face and the second layer. And if there's a big differential, we might put a slight gap. And it might even not be fiber filled for the reasons of hydrogen. It might be a burnout material. But it's a gap that we know that closes at your operating temperature. Then the outer layer up against the pressure vessel, we have a compressible fiber. Incidentally, within that 15 inches of refractory depth, where that fiber exists up against the vessel wall, now we're below the hydrogen silica reduction temperatures, so we can exist a fiber there. that stays in place and does its job. But again, we have to make sure we understand fiber can't compress to nothing. Different fiber densities can compress at different ratios. So that all has to be designed for and accounted for in the thermal calculations. But just to put a real world spin on this, so just to highlight the point, the method on the left assumes that individual shapes are expanding. They can close gaps. The method on the right really relies on the fact that the wall, the hot face, works as a big networked cylinder, big networked assembly, right? And we're not getting individual movement substantially between bricks. So in fact, what we see is when you view any given hot face lining after use, you'll see 3 or 4 radial cracks go down the wall of a given generator. And you know it's a networked assembly, it's not individual bricks, because you know some of the openings might follow a joint, but other ones just cut right down through a brick. So this thing doesn't care if it's an individual brick. It's just a solid wall of refractory that's expanding and contracting. We also know that if you wanted those pieces to slide together, like the European radial expansion design, that you could actually get such high coefficients of friction that the force you calculate to slide some of these bricks in the lower wall together with all the bricks stacked on top would actually exceed their crushing strength. So before you would close that joint, you would break the brick and crush it, which is what we see in some of these places that do this concept. So here's where the methodology is applied in 2 different units. And in these units, after a couple of years of operation, I can still see the open joints as installed. They may have changed in dimension slightly, but they're all still there. So, true, there's not a huge thermal gradient over the hot face, but you're letting hot gas right past it into your second and third layer. It becomes an issue. Not only that, but when the joints remain open, you're not actually addressing the need for radial expansion. So the lining, this very same lining that we saw all the open radial joints in, we started to take down the hot face, and we saw the brick layer right behind it was all crushed to hell. And in fact, the top of the sidewall of this unit was coming in because it started to come in and the broken bricks started falling down between the gaps between the hot face and the second layer and didn't let the hot face layer move back. It just became an ever-driving scenario where the wall started to collapse. Similar issue, right? So again, the inner layer expands more than the outer layer. So in an ideal sense, you would hope that the inner layer is going to push on the outer layer, and just all the little bricks individually are going to kind of open up and not open up too much, let the hot gas pass through. But again, these are networked assemblies. They're not individual bricks. More than typically happens is, this is a worst case scenario on the right side where the hot face might expand and take all of its opening in one joint. Realistically, it might be distributed over 3 or 4 joints, but you're popping open the outer ring segments when the hot face expands. And again, so if the hot face gas or the hot gases find a way past the hot face and align with these joints, you have a hot spot. And now you're shutting down. And now we're relining. What could be otherwise perfectly good brick, just out of alignment. So some ways to dissuade this is we use things like shiplap joints, right? And in fact, in the worst cases, in some applications, we can actually shiplap both the vertical joints as well as the horizontal joints. So like in what's pictured here, I have a hot face and a second layer that are shiplapped in 2 directions that give me this cross-woven pattern. So no matter how this thing expands or contracts, unless any one joint expands or contracts more than an inch, I still have a tortuous joint for hot gas to go through. So this, in fact, in many of the revisions we've done over the last couple of years, a lot of your units you have now the second layer as a shiplap, so that hot face doesn't push open the outer layer bricks. Incidentally, they're larger shapes also, so you have less joints, less opportunity to do so as well. John talked about tongue and groove. Tongue and groove has their place. I'm not a fan of tongue and groove, and that is because it helps during installation, but physically happens is if you get too much expansion in one area, and in some of these units you might be expanding from the bottom of a POX train all the way to the top, you might be expanding a couple of inches. So things, in the center throat section, the choke section, might actually separate. And if they separate, and as they cool, become misaligned, you can start to get gaps that now the tongue and groove doesn't allow things to close back up. So I find that the shiplap is much more robust in terms of when you have separations, allowing itself to close back up, which is why we've instituted it successfully in many of your designs. This is going to go specifically to Tim's flexible thermocouple and Lionel's question. So something that would work quite well with Tim's thermocouple probe design is we've come up with the concept of nesting the thermocouple blocks. So instead of the thermocouple penetration areas inside your sidewalls just being one more piece of a concentric layer that has a gap between layers, we actually produce a nesting offset in the back of each block that sits inside the next block, and the gaps around it are designed to accommodate the expansion between the layers. What's nice about this is not only does it give you more of a tortuous shiplap-like design between these blocks where you have a penetration where gas could be working through linings and layers, but it also, from a top-down perspective, locks your bricks in for many thermal cycles coming out of alignment. So your alignment issues are much better when you lock these bricks in. This is a big one. This is a big one, guys. So everybody wants to go do a partial repair. I say partial repair. I understand we might do a dome, we might do a cone, various sections, right? That's par for the course, right, in terms of what we're doing today. But what you have to recognize is you're given an initial refractory design, and it has initial thermal expansion joints all throughout the different layers, because these different layers are for the first time going to go from cold to hot and have to all move around together. But what happens if we're going to just put a cone inside of the existing sidewall? That sidewall, all those layers have already moved outwards. They got hot. As we saw that sidewalls have these cracks that develop because of the radial expansion, these sidewalls don't completely move back in when they get cold, right? The vessel to some degree might drive a few millimeters of movement back in, but it has to compress the fiber and start to compel all these different layers to move uniformly. Realistically, we measure any given POX unit, the diameter is a ½ inch, quarter inch larger than what it started out as. It's not because you lost a ½ inch of brick, it's because it thermally expanded and stayed there. Now when you go to install the cone, with the tight tolerances that Saint-Gobain gave you for all the different shapes, the installer left unchecked is going to say, well, I want this cone to fit tightly inside the sidewall because that's my job. They've done you a complete bad thing. They've done a disservice to you. If you install that cone tightly inside the sidewall and don't allow for an additional expansion gap because that cone has to initially grow, where the sidewalls already have, your cone starts to peel itself apart. The old Texaco refractory supervisor, Ken Young, called it the blooming onion effect. Right? What causes these cones just to peel apart and make all these radial hoop joints and hoop stresses? It's not allowing enough radial expansion between that and the wall. We see this in other areas as well. We see this in areas around the transition blocks. We see this in areas up around the domes. You have to be cognizant of what you're leaving in place and how much it's moved, and then what you're putting in and how much that has to move. And you have to have, ultimately, a refractory engineer go back and run the calculations to say, this has moved this much, this is going to move this much, therefore this is the new gap. No better practice. I was just at Duke Energy a few months ago. So I was there 2 years ago, and I said, hey, when you guys put that sidewall back in, recognize the outer sidewalls have moved. And they said, okay, what should we do? I said, well, you should put a little bit of a gap between the back of the hot face and the outer two layers of sidewall that you're keeping in. and we actually calculate, it was a substantial gap. It was 5/8 of an inch gap. And they said, oh, we don't like this. 5/8 of an inch, that's a big gap. We don't want hot gas flow. I said, trust me, here's the calculations. 5/8 is conservative. It actually moves about 3/4 of a unit that size. They put in a 5/8 inch gap in the lower sidewall. The next time they came in, they only lost a 1/2 inch of brick thickness over a 1.5 years of operation, which is incredible for a slagging gasifier. They're going to get almost 6-year refractory life in a slagging gasifier, which is double almost what anybody's gotten. Incidentally, in the same sidewall area, after I left, the installer in the upper sidewall said, yeah, but the upper sidewall has to be tight. Let's get rid of that 5/8 of an inch gap and brick it tight. They bricked it tight. You can see right here where that started. They lost about 1.5 inches of extra brick where that was bricked tightly versus where they left the appropriate expansion gap. And incidentally, all the outer layer bricks they exposed were all crushed as well. So something has to give, right? You're building up stress in the lighting system. In this case, you popped all the slag penetrated areas of the bricks off and lost substantial brick thickness. But in some cases, you just crush the outer layer, which becomes a proposition for a reline. Again, this is germane to you guys with POX units, not solids units. When you start crushing up that outer IFB layer, you're going to reline. You're going to get hot spots. We're going to pull out perfectly good hot face brick, full 4, 5, 6 inches thick. But we're going to reline it because you've crushed your outer layer, because you installed your hot face too tightly. So a couple of tools we've developed. I have examples on my back table. I'd be happy to run through these. We have a radar scanning technique now, based very similar to ground penetrating radar, where we can actually scan the refractory lining hot face. We can see the layers kind of depth-wise going in, so we can understand if you have voids or defects inside those layers. We can understand how much expansion you might still have from the fiber layer. So this is the hot face layer, and a small gap that developed when it cooled between the hot face layer and the second layer. This light line here represents the bubble layer and the IFB, and this represents the big fiber layer between the vessel wall, which is here, and then you get just noise in the scan. And this can actually scan, 4 feet of refractory. We're really scanning 1.5 feet. So we can start to see, without taking down hot faces, to look for hot gaps and look for spaces, right? Because often forensically, that's what we end up doing. Is somebody says, I have a hot spot, it must be hot gas. It's not apparent on the inside, go find it. You start taking out all these good bricks with the hopes of finding a void. Now we can look for voids without taking those bricks out. I use this technique. So if you have a quench upset, or if you have a tube inlet leak where you get water inside the unit, so the way these radar waves work is they use the dielectric properties of the material to look at how fast the radio waves travel through the material to give you a reflection of different dielectric surfaces and give you these depth maps. It happens the dielectric constant of that material changes pretty substantially if you introduce something like water in the porosity. So since Lionel had an issue where he got some water in the bottom of his ash pot, he drained all of it out, let it set for a couple of days. So on the inside, it looks nice and dry and good, but we don't know how much water got where in the backup layer, because we could have still thousands of gallons of water in the backup layer that we better figure out, because if we heat up and that turns to steam, they're going to blow out the refractory. So I brought the tool in, we scanned the wall, and we were able to figure out what depth the water traveled in the backup layer, and we're able to suggest that a curing schedule and a maintenance schedule that address that quite successfully. Another tool used across industries these days is we digitally scan. I have my digital scanner here. I can scan any one of you and make a little 3D model, and you can put it on your desk. But I use it to scan complicated and refractory linings that I can compare the point cloud from one instance to another and see on a very nuanced way how all these different materials are moving with respect to one another. Or with respect to a slagging gasifier where you're losing thickness, we get a very detailed map of the thickness loss, like Tim's IR cameras, on a pixel by pixel basis throughout the unit as opposed to going in and dropping down in a bosun's chair and taking all these differential measurements and trying to come up with some operating or maintenance philosophy based on that. This is all about, in my view, giving data to you guys and benchmarking what was last time and what is this time. Because you shouldn't be beholden to any one person. You shouldn't be beholden to me or anybody else who says, I know 100% of what it is you should do. I think I have a pretty good track record, but that said, I want to give you guys data, share with you what I'm looking at, and start to make these maintenance decisions together. So I feel that my reference list is quite old. It's probably twice as long now. But I feel that I mitigate refractory risk in a number of ways. So I tend to be involved in the upfront design. We do design reviews. Share with you guys the data, the calculations. Get involved then, go into the manufacturers, right? Agnostic, right? I like to work with Sacred Bond, but I can work with anybody. Make sure that they're supplying to the specifications of the design. This is something that more of you should consider. Some of you have been considering it now, but when you're purchasing $1 million of refractory, go take a plane ride and go look at the stuff and see how it's going to fit. You know the delays and the problems it's going to cause if you find out it's not going to fit when you're in the middle of your outage, right? So go take some time. That same scanner tool I just showed you, I take it with me. I'll tell you, I scan the shapes. I compare it right to the CAD model. It immediately glows green if it's in the 1 millimeter tolerance. Versus it tells me, hey, these shapes aren't going to fit together as I expect them to. We better remake or mitigate or do something to these shapes, right? Good use of technology here that actually avoids having to get into some of these complicated pre-assemblies. If we can precisely measure all these shapes and get all the curvatures and all the different dimensions that we can't otherwise measure with the parent calipers. Incidentally, use it on a feed injector tip, right? Concentricity and things. You guys have time-tested, honed methods with your gauges to get those concentricities right. And again, you can catalog and document these point cloud spaces to make sure everything is perfectly correct. My last slide will be something about that. Again, data-driven inspections. I share with you my data. We make the decisions together in terms of what makes sense. We have discussions. I tell you what I think. I could be wrong. Here's what the data shows, right? Let's roll the dice together if it's a dice roll, right? But all these tool sets are available with you. Installation quality control, the most boring part of my job, sitting there watching people put refractory in, but it's important. It's important to get the gaps right. Things fall apart. It's important to make sure the designs are interpreted correctly. What you don't get, if you just hire some guy to come in and look at the drawing and say, well, it says to do that, is you get no feedback from the field back to the design. So I like to come in before you do a tear out, and I like to sit there and watch you take the lining apart. What part worked well, what part did not work well, and feed that back into the design for next time. Again, I can't solve a problem 9 times out of 10 right then, but I could certainly understand the problem, characterize the problem, and solve it for the next time, and make the next time that much better. Continuous improvement, right? And obviously, I understand some of the synergies of some of this equipment, right? The way the feed injector fits and the way it operates around the refractory, how the refractories sit around the tube sheet, quench ring, all these different parts. And lastly, obviously safety-oriented and fully insured. Get inside your front gate. I must say my insurance premiums are a nightmare, but the things I do for you. Everybody I've engaged so far has remained persistent and a promoter. And frankly, I have to be careful on how many more people I engage. Otherwise, I can't give good service to the people I am hopefully providing good service to. And it's the same question I posed to you last time. Ultimately, can you afford not to do some of these things? Right? Yeah, we can save 50 grand, 100 grand by not having Wade sit there for some period of time, for some number of months, right? But what's going to happen if you just used all your refractory, you did something wrong, but now you're shut down for 6 months? A pretty cheap insurance policy. It's my last slide. an example of a synergy that I could see us working on here in our little Syngas group. Right, so problem statement. So feed injectors, right? We've got, as Andy said, concentric gaps. We have retractions, right? Little minor changes. So obviously all these gaps we're talking about are the cross-sectional areas that divide into the gas flow that set your velocity for the process volume. We have certain velocity limits that we think we know pretty well. Sometimes we don't know so well. We're still experimenting with. But when you talk about things like non-uniform or concentric annular gaps, you talk about, turn down injector designs, things like that. Let's start to use our head on some of these things, right? Understand that if you have a concentric gap between two tips, which is always measured by some fraction of millimeters, right? We're not talking huge concentric gaps. In some cases in the smaller injectors is a quarter inch, 3/8 of an inch. So if you're shifted by 1 or 2 millimeters, sorry for switching units, if you're shifted by 1/16 of an inch, one side to another, take it away a 1/16 on this side, give it a 1/16 to the other side. Well, the cross-sectional area changes by the square of the radius, right? So you could literally induce twice the flow on one side of the injector than the other side, right? Just by a couple of millimeter changes in concentricity. And again, these guys do an impeccable job, A&A, of making sure that out of the box, it's where it needs to be. Who's to say it's where you think it is after multiple thermal cycles, operations? Who's to say it's where you think it is based on what you think the temperatures of your injector are, right? So one of the things we can imagine doing is, okay, I'm going to engage A&A, and we're going to do some things with an injector. There's actually some things where we can make it tunable, right? Maybe this isn't the injector you run as a production injector. We could certainly make some different gasket thicknesses and iterate, what our expansion gaps, our annular gaps are going to be. I'm going to get with Tim. Tim's going to instrument that injector. It's also going to give me a bunch of thermocouple wire. And when I install the next refractory lining, I'm going to run some thermocouple wire behind the brick, poke it out in different areas of the hot face, very minuscule, pinpoints, right? Now instead of the 1 or 2 elevations in the reactor where I get process feedback, I'm going to get 10 or 20. Now when I start to look at velocity flows and turn down and all these different things you guys want to do with the injector, I can start to develop a temperature map inside the unit to say, hey, for your process volume, for your configuration, this is how much you can safely turn down, turn up, turn sideways, whatever, right? You don't want to be causing damage by just applying general rules of thumb that we think apply to every single injector configuration and gasifier. So we'd monitor the temperatures. These thermocouples would be essentially sacrificial. They might run for a month or so. We'd get a hell of a lot of process data, wouldn't we? We learn all kinds of things we don't know today about your reactor. Just an example. Appreciate your time. Is there any questions that I can handle right now? I substantially answered everything. Awesome. Okay, cool. No, I appreciate it, guys. Thank you.